Hello. Hey guys. So while we're waiting, as you can see, I got a haircut. My hair was getting so long that I had to put it up in a ponytail because it would get in my eyes. So got a haircut today. It's a lot better now. I can actually see things. So yeah, if you were wondering. All right, one more minute and then I'll get going. Hello. Hi, Michael. Alrighty. People are coming in now, so let me share my screen. So you can see the PowerPoint. All right, so how about one more minute and then we'll get started. Okay, let's get going. So this week is week 12 of physics, and it is the first week of rotational motion. So I think we're going to have 2 weeks in total. So after this week, we're going to have another week of rotational motion. This is the first week of rotational motion. All right. So the topics are, what is rotational motion? We're going to do kinematics with rotational motion, what we call the moment of inertia. We're going to go over torque, and then angular dynamics. All right. So first of all, what is rotational motion? Well, what have we been talking about for the entirety of this course so far? For the entirety of this course, we've only been talking about what we call translational motion. I'll write that here. Translational. Translational motion is where an object moves in a straight line. For example, we had a box sliding along the floor. And we had a box falling onto a spring. And all these things happen in relatively a straight formation. It's along a straight line, okay? So rotational motion is the opposite of that. Rotational motion is when things rotate, when things spin. We went over one specific aspect of rotational motion back in week 5, where we had centripetal motion, right? Where a ball swings on a string around and around. That's one example of rotational motion. But we have a lot of different kinds of rotational motion. So for example, we could have, if you've ever been to a Chinese restaurant and they have a big round table, and in the middle they have a little spinny thing that can spin around, and it brings your food around the table. So if that thing starts spinning, then that's what we call rotational motion. Things can spin like that. And also in medicine, for a blood separator, we have these these circles, and they put the blood in little tubes like this, and it spins super duper fast. Okay, so those are all examples of rotational motion. Okay, and some more types of rotational motion. I think a common example is a carousel at the fair. Right, you guys know what a carousel is? It spins around with little animals on it. Okay, so these are all examples of rotational motion. So what defines rotational motion? How do we know if something is rotating? Well, obviously we know something is rotating if it's spinning around on some kind of axis. So what do I mean by axis? Well, we have what we call the axis of rotation. And this basically defines around, it's kind of like a pivot point in which the object will rotate around. For example, if we had at the Chinese restaurant again, the little spinny thing in the middle, if it spins like this, then it's spinning around its center. So in this case, the axis of rotation is downward, perpendicular to the spinny thing. All right, and we can have many different axes of rotation. Another example is if we have a door, for example. If you have a door like this, the hinges basically secure the door in that axis of rotation. The axis is right here, and the door can spin like this. Okay, so most of the time when you see a problem, it's gonna define the axis of rotation. Mostly it's gonna be like an anchor point. And if you anchor an object to that axis of rotation, it has to rotate around that point. Okay, but if there's no axis of rotation defined, then the object will rotate around its center of mass. For example, if I had, I don't know, a cylinder, okay, just like the Chinese thing, all right, if I were to just spin it like this, it will rotate around its center of mass, around this. So the center of mass automatically turns into the pivot point. So if the door wasn't secured to the hinge, like in this example, if the hinges weren't there to secure the axis of rotation right there, then the door would spin around its center of mass like this. All right. So when a pivot point or an axis of rotation is defined, which means there's a hinge there or whatever, then the object will revolve around that hinge. But if there's no axis of rotation, it will revolve around its center of mass. Okay, so that's how rotational motion works. So now let's go deeper into the physics of rotational motion. So just like how we started this entire class with kinematics with translational motion, we're going to go over kinematics with rotational motion. So the cool thing for rotational motion is that the physics doesn't really change between rotational and translational motion. All the formulas you learned so far, they're also valid for rotational motion. So as you know, we have some kinematic formulas. V squared equals V0 squared plus 2AD. We also have kinetic energy. These are all formulas you've memorized, right, from all the past lessons. And these formulas apply also to rotational motion. It doesn't change. You can use these exact same formulas. And that's the pretty cool thing about rotational motion. You don't really have to memorize new formulas in this kind of aspect. But the problem is, although the formulas are still standard, the variables inside the formulas need to be tweaked a little bit. So what do I mean here? Well, translational motion, again, is in a straight line, right? For example, regular velocity is a straight line vector. Regular velocity is a straight line, right? But when things rotate, they go in circles. So you can't really directly relate translational functions or translational equations like this directly to rotational motion. You gotta tweak the velocity a little bit so that it can be defined to work with rotational motion, right? Because the velocity as it is right now, we can only use it with a straight line, translational motion. But we have to alter this a little bit so that we can use it with rotational motion. So basically, in the end, the formulas are still the same, but we have to swap out some of these variables for variables that will work with rotational motion, okay? So I'm going to call these new variables angular quantities. For example, velocity, just normal velocity, is a translational quantity. And we're going to have to turn this into an angular quantity so we can use it with angular motion, all right? But all these formulas are still the same. All we need to do is swap out these variables for things that will work better with angular motion, okay? So one example of which is just plane distance, right? Plane distance is a straight line, right? We can't really directly apply this to angular motion yet. So what do we use? What's our angular quantity for distance? Like, how do we swap this out for something else? Well, in angular motion, we're going to use the angle as a distance, right? If you go a certain angle, then that kind of counts as your distance, all right? So instead of distance d, we're going to be using an angle theta. Angle theta is basically the angular quantity in representation of distance, okay? So for example, in the equation, v squared equals v0 squared plus 2ad. To use this with angular motion, we just have to swap the distance out with theta, okay? So we kind of swap these values out for one another so we can use this with rotational motion. So instead of distance, we use theta for rotational motion. So what's the relationship between distance and theta? Well, if we have the simplest case where we have a ball spinning on a string, then the angular distance is theta, right? But we also have a linear distance this ball has traveled as well. Because as you can see here, it's traveled in this arc. This arc is kind of like the translational motion it's gone through, okay? But it's gone through an angle of theta. Well, what if we draw another ball so that it's kind of closer to the string, closer to the center? Well, now the distance is a little smaller, right? The distance of this ball is smaller than the distance of this ball. But the angular distance they've both gone through is the exact same. They've gone through the exact same angle. But how are their distances different? Well, we have a formula that relates theta to the distance traveled. And this is distance equals radius times theta. And radius is the radius of rotation right here. So as you can see here, if there's a smaller radius, then the distance it travels is different, even if theta is the same, okay? So this is how we relate distance to theta. So this is kind of like we're relating the translational quantity to the angular quantity. So distance equals r times theta, okay? So are there any questions about this? So we've kind of swapped out distance for theta now. Well, let's go on to some other things, right? Normal velocity is normal distance over time. But we can't use normal distance with rotational motion, right? Because rotational motion goes in a circle. We have to swap this out for theta over time. And this is where we get angular velocity. Angular velocity is the velocity that works for angles, okay? So regular v is d over t. Angular velocity is theta over t. And the symbol we use for angular velocity is the Greek letter omega. It kind of looks like a W, okay? It's called omega. And personally, I'll just call it W for simplicity's sake, because why not? It's a W, okay? So angular velocity is represented with a W, all right? So back to the equation v squared equals v0 squared plus 2ad. We would swap out d for theta. We swap out v for w, okay? So that's basically how it works, all right? And just like how we've related normal distance to the angular distance, we can relate normal velocity to angular velocity by the same reasoning, r times w. So basically, the translational motion equals the radius times the angular motion. Okay, so this might be a little confusing, so let me draw it out once again with our ball. So the ball on a string, it's going at angular velocity. Okay, it's spinning around at an angular velocity. The angular velocity is basically how fast the string is going around in a circle. Okay, but how fast the ball is going instantaneously, if it's up here, then it's going at some kind of v. But if it were down here, then it would be going a lot slower, right? Naturally, because it's closer to the center of rotation. Even though the angular velocity is the same, the translational velocity depends on the distance r, okay? So that's how we would relate angular to translational velocity. So similarly, we have angular acceleration. Normal acceleration is change in velocity over time. So angular velocity is change in angular velocity. Angular acceleration, I mean, is equal to change in angular velocity over time. And the symbol we use to represent angular acceleration is alpha, the Greek letter alpha, okay? So it kind of looks like that. So don't get confused when you write out your equations. So be careful when you're drawing out these letters because they look very similar. So I would recommend drawing them like very differently, if you will, when you're doing your equations. So back to the equation, v squared equals v0 squared plus 2ad. To completely transform this into angular form, we would do w squared equals w0 squared plus 2 alpha theta. Okay, we basically swapped out the translational quantities for angular quantities. Okay, and all the kinematics equations will work this way. All right, we have another one which is d equals v0t plus 2a plus 1/2 at squared. We would have theta equals w0t plus 1/2 alpha t squared. So we can convert all of our translational kinematic equations into angular form by doing this process, by swapping out each and every one of the variables. Okay, and just like with the relationship between distance and theta and velocity and regular velocity, you also have regular acceleration equals radius times alpha. Okay, so these are basically the formulas you need to know that relates the translational quantities to the rotational quantities. And then another thing you need to know is just swap out the variables in your equations so you can work them with your rotational problems, okay? And one misconception a lot of people have is with the acceleration here. This normal acceleration, a lot of people think that it's referring to, well, since it's rotating, they think it's referring to centripetal acceleration. But no, this acceleration here, it is not the centripetal acceleration. Let me explain why, okay? Any object that goes around in the circle has to have centripetal acceleration, right? That's what makes it go in a circle. And even if it has constant velocity, it's still going to have centripetal acceleration, okay? But if there's constant velocity, if velocity is constant, then omega is constant. So that means there can't be any angular acceleration, right? So that means that these two things cannot be, angular acceleration can't be directly related to centripetal acceleration. Angular acceleration is actually how much faster the object is spinning around. For example, it might be spinning quite slowly initially, and then it goes faster and faster and faster and faster. Okay, so the acceleration is not the centripetal acceleration, but rather the acceleration in this direction, which we call tangential acceleration. So the acceleration used in this equation right here must be the acceleration over here, tangential acceleration, not centripetal acceleration. Okay? So basically, centripetal acceleration doesn't really have anything to do with this. Okay? Are there any questions? Alrighty. Let's do some problems. We have 4 problems here. And I'll give you guys 5 minutes to do these.
What is RAD over S?
What?
What's RAD over S?
Could you repeat that again? My computer's a little bad.
RAD over S.
RAD over S, it's radians. Okay, so sorry if I forgot to mention this again. Whenever we use theta and omega and alpha, we have to use radians to represent angular measurements. Okay, so we can't use degrees. We use radians for our angular measurements. So if you don't really know what a radian is, there are 2 pi radians equal to 360 degrees. All right, one more minute. All right, so that's time. And for the first problem, Max will be explaining it. So go ahead, Max.
Okay, so for the first question, so here we are, I'll type it out. So then, wait, how do I write R? It would equal, since it has an angular speed of 8 radians per second, so then it would just be on the top, it would be 8 minus 0. And then it's 4 seconds, so then it should be 4 minus 0. And then if you just simply calculate it, it would just be 2 radians per second.
Yep, that's correct. All right, so you basically did angular acceleration equals change in angular velocity over time, and then just plug numbers in and you'll get the answer. And for the second one, a disk initially at rest accelerates to an angular speed of 5 radians a second. It takes it 3 revolutions. So Fiona raised her hand. Do you have a question?
Shouldn't it be radians over seconds squared?
Oh yeah, sorry about that. That's correct. Okay, so make sure you get your units right. Okay, so a disk initially at rest accelerates to 5 radians a second. Then it takes the disk 3 revolutions to accelerate to this speed. What was the acceleration? Well, we have acceleration, speed, and then some kind of distance. So the equation we're going to think about is v squared equals v0 squared plus 2/8d. If we convert this to angular form, we'll have w squared equals w0 squared plus 2 alpha theta. Okay, well, right now we have our velocity in the right form, but our distance is in revolutions. It's not in radians yet. So we have to first convert this to radians, and then we can apply our formula. So how many radians are in 1 revolution? 1 revolution is a whole circle, so 2 pi radians in 1 revolution. So 6 pi radians in 3 revolutions. Okay, so now let's plug our values in here. Our final speed is 5. 5 squared equals 0 squared plus 2 alpha 6 pi. Okay, so now we just need to solve. So it's 25 divided by 2 divided by 6 divided by pi. So alpha is 0.66 radians a second squared. Okay, and for the next one, initially a disk spins at 4 radians a second, then it accelerates to 6 radians a second in the span of 3 seconds. How many revolutions did it spin in this time? Well, this one is a little trickier, right? We have initial and a final speed, but then we need to find, we have a time, and then we need to find revolutions. How do we do this one? Well, first we can find our acceleration, because we know that acceleration is change in velocity over time. So our acceleration is 2/3, 0.67. So now we have our acceleration. So what we can do is we can apply the formula theta equals w0 squared, w0t plus 1/2 alpha t squared. So theta equals 4 times 3 plus 1/2 0.67 times 3 times 3. All right, so what will that be? Let me first calculate that quickly. That should be 15 radians. Okay, so there are 2 steps to this kinematics problem. All right. So now we have a last one. A ball is spinning with angular velocity 5 radians a second. What is the frequency and period of rotation? Well, if we think all the way back to our 5th week of class, frequency is how many revolutions per second. And the period is how much time it takes to do 1 revolution. Well, let's first calculate period. Period, if you may remember, period is basically a unit of time. Period basically means how much time does it take for this to go around 1 time. So distance, angular distance over velocity, angular velocity. All right. So that's basically the period. So what is the oops, someone has, oh, yep, Max said the answer to the other question here. Theta is not actually 15 radians. Theta is 15 radians, but we have to convert this to revolutions, right? So it's going to be 15 over 2 pi revolutions. Thanks for catching that, Max. All right. Now for the last one, how much time does it take to go around in one circle? Well, it needs to go 2 pi radians. And it's going at 5 radians a second. So that's just the answer, 2 pi over 5. Okay, are there any questions? All right, let's skip these. So now let's go on to moment of inertia. So first, ignore the diagram to the right. So what is moment of inertia? Well, as I said from the beginning of class, we need to replace values in our equations with values that we can use for angular motion. For example, we have F equals ma, right? A, we know we can replace this with alpha, but we don't know what we replace with m or f yet. So for angular motion, what we replace with mass is what we call the moment of inertia. We label that with an I. Okay, so we replace the mass with moment of inertia. I don't know why it's called moment of inertia. Honestly, I don't know why. So that's just the way it is. Okay, so we're going to replace mass in all our equations with what we call the moment of inertia. Okay, so for any equation involving mass, F equals ma, Ke equals 1/2 mv squared. We have to replace all the masses here with inertia. Okay, so how do we find the inertia of an object? Well, we have 2 types of inertia we could calculate. First, we have the inertia of point masses. The inertia of point masses, so the definition of the inertia of a point mass is I equals mr squared. Okay, so for example, if we have the axis of rotation right here, radius r, and the point mass has mass m, then the inertia it has is its mass times its times the radius squared. Okay, so that's the definition of inertia. So whenever we're doing the physics with a point mass, then we're going to have to replace mass in the equation with mr squared. Okay, so Fiona, do you have a question?
Yeah, is that what's a point mass?
So point mass is kind of like a small mass, okay? It could be a small ball. It just needs to be, like, the radius of the ball needs to be relatively smaller than the radius of rotation, okay? So basically, that's what a point mass is. We can consider it as 1 point, okay? So the formula for the inertia of a point mass is its mass times the radius r squared. All right? So what this means is that, for example, if we had the equation for kinetic energy, 1/2 mv squared, right? If we turn this into angular form, we're going to have to use 1/2 iw squared because we replace v with w. And then we plug in mr squared as I in here, okay? So that's basically how we do inertia with a point mass, okay? And then the other type of inertia we have is in the diagram on the right. So the diagram on the right, as you can see, we have a lot of common shapes, right? We have a cylinder, we have a thin hoop, we have a solid ball, all those things, okay? And on this diagram, we can see that we have values for inertia of each of these objects. Okay, so this is kind of like the second type of inertia we have for like common shapes, like a rod, a ball, a cylinder. Okay, so for any physics we do with a cylinder, we're going to have to plug in I as 1/2 mr squared. And if you're wondering about how you would derive each of these formulas, you would have to use calculus. Okay, you would have to do an integral and all that kind of stuff. So for now, just memorize these things. Okay, so I would recommend maybe taking a screenshot and writing these down as common values for inertia. Okay, so whenever we do physics with any of these specific types of shapes, then we're going to have to use the right type of inertia to do our calculations with it. Okay, and you may be asking, why don't we just use mass in our equations, right? Mass isn't a vector. Mass doesn't care about if we're going in a straight line or we're going around in a circle. Why do we have to use inertia? Well, as you can see in inertia, we have radius considered in here. And the reason behind this is that the physics behind a rotating object really depends on how the mass is distributed around the object. Okay? So as you can see here, right here, comparing the rods through the center and the end, the rod through the center has less inertia than the rod through the end. Okay? So this is because the mass is distributed differently around these two objects. Okay? So the distance the mass is away from the center of rotation, we have to consider that into account for our rotating masses. Okay? So those are the inertias for common types of objects. And I would recommend memorizing those because when you go to a test, they're not going to give you that information. Okay? So some other things you need to know about inertia are if you have multiple objects in the system, like for example, let's say we have two cylinders stacked on top of each other like this, and they're going through the same axis of rotation. What's the inertia of this entire system? Well, the cool thing about inertia is that for any kind of combination of objects or point masses or whatever like that, as long as you add up all the inertias of each individual object, you'll get to the final inertia of the whole thing. Okay, so the better formula for the inertia of a system is the sum of all the inertias of each object. Okay, so you take the inertia of, for example, the top cylinder, you take the inertia of the bottom, and you add them all together, and you'll get the inertia of the whole system. Okay, so that's basically the formula for like if you had multiple objects in the system. Okay, so are there any questions about this right now? Okay, so before we go on, we have two critical formulas for inertia. So as you can see on our table for common values for inertia, for the cylinder, the axis goes through the center of the cylinder. Then hoop as well, solid ball as well, and once again, rod through center. Okay, but if the axis of rotation was in a different place, then the mass would be distributed differently, and then the inertia would change. Okay, so as you can see here, for the rod through the center versus the rod through the end, if I moved the center of rotation to a different location, then the inertia changes. So how do we calculate the change in this inertia based on where the axis of rotation moves? Well, we have a formula for this. We have, it's called inertia nu equals inertia 0 plus md squared. So let me break down this formula for a second. So let's go to our example for a cylinder. We know that the inertia through the center, let's call this I0. Okay? If we move the axis of rotation so that it's here now, then we have a new moment of inertia. Okay? So if we add I0 to this quantity md squared, we'll get to our new inertia. Okay? So what is d? What is m? D is the distance between the two axes of rotation. It's the distance between the old one and the new one. Okay? And then m is just the mass of the object. All right, so this basically, this formula is pretty handy in problems where the axis of rotation is not in the location given by these formulas. Okay, these formulas only work if the axis of rotation is directly where it's labeled in the diagram. Like for a cylinder, it has to be in the middle for it to be 1/2 mr squared. If it's on the side or a distance off of the center, then you would have to use this formula to calculate the new inertia. Okay? Are there any questions about this?
Wait, but if the moment of inertia is substituting mass, then why is there like mass in
Well,
the
yeah, for equations, we're going to have to use inertia, but inertia still depends on the mass, except we need to consider the radius as well. So that's basically the critical part. Inertia needs to consider the radius. Inertia needs to consider how the mass is distributed. In translational motion, if we had a box, we didn't really care about where the mass was in that box. Okay? So basically, we use inertia. Inertia still includes mass in it, but inertia also includes the radius. Okay, so that's why we use inertia. All right? So another formula we have for inertia, a really handy dandy formula you're going to use quite a lot, is Iz equals Ix plus Iy. So let me break this formula down for you. Let's go back to our cylinder. Okay. Well, a cylinder is a three-dimensional object, right? We can have a z dimension, an x dimension, and a y dimension. And as you can see here, we have one dimension that goes through the cylinder like this. We have one dimension that goes like that. And finally, one dimension that goes like that. So let's label this the z-axis, the y-axis, and the x-axis. Okay, so as you can see here, the y-axis and the x-axis are what we call parallel to the plane of the cylinder. Okay, they're parallel to the faces. Okay, but then z-axis, that's the different axis. This axis is going perpendicularly to the cylinder. It's going perpendicularly to the faces of the cylinder. Okay, and the formula here says that the inertia through an axis of rotation along the z-axis equals to the inertia along the x plus the inertia along the y. So if we add the inertia on this axis to the inertia on this axis, we get to the inertia on this axis. So the thing is, the inertia of an object depends on where the axis is rotated, right? Just like with these two objects here. And if we put it differently, if we put the axis of rotation differently along the object, then the inertia is going to change. And this formula basically relates the perpendicular inertia to the parallel inertia. So you could write this as I perpendicular to the surface equals I parallel 1 plus I parallel 2. Okay? So this formula relates the inertias between the three dimensions. Okay? Are there any questions about this? Alrighty, so that's basically all you need to know about inertia. Okay, so to recap, for rotational motion, inertia is a substitute for mass. For point mass, inertia equals mr squared. And for a more complex shape, inertia is based on these things. Okay, and then we have two formulas for inertia, which is I nu equals I0 plus md squared. So this formula basically helps you solve for inertia if the axis of rotation is in a different location. Okay, and then we have one last thing, which is Iz equals Ix plus Iy. Okay, this relates the inertia between all three dimensions in space. Okay, so let's do some problems here. Two problems. I don't think these should take that long, so 3 minutes. Someone's asked for the unit for moment of inertia. The unit, well, we're just going to use unit analysis. Remember how inertia is mr squared? Then m is in kilograms, r is in meters. So kilogram times meter squared. Okay? That's the unit for inertia. All right, 1 more minute. Alrighty. So for the first one, a point mass of mass 6 kilograms is 1 meter away from its axis of rotation. What's the moment of inertia about that axis? Well, the moment of inertia for a point mass is given by mr squared. So m times r squared, 6 kilograms per meter squared. 6 kilograms times meter squared. All right, for the second one, 3 point masses orbit around a common axis of rotation. And we have all this information. So what's the combined moment of inertia of the system? Remember that whenever we calculate a system of objects and the inertia around a bunch of different objects, all we need to do is calculate the inertia for each individual one and then add them all together. Okay, so let's calculate the inertia for the first one, which is 6 times 2 times 2. Add that to 3 times 6 times 6. Add that to 0.5 times 10 times 10. We get 182. Kilograms times meter squared. Okay, any questions? All right, more problems here. We've got 4 problems. These are kind of like direct applications of the inertia for common objects. Okay, so I think you guys should only need to spend around 3 minutes on these. All right, 1 more minute. All right, so let me go over these problems now. So for the first one, the formula for a cylinder is 1/2 mr squared. Plugging this in, I think we have 0.5 times 10, that's 0.3 times 0.3, 0.45. Okay, for the second one, solid bowling ball means it's filled in, so it's 2/5 mr squared. Plugging values in, we get 0.64. Now for a hollow ball, we have 2/3 mr squared. If we plug values in, let me first do this real quick. It's actually gonna be 5.33 times 10 to the -6. Okay, very, very small. So now around a 4 kilogram rod, through the center, it's 1/2 ml squared, 1/12 actually. So that's gonna be 4 divided by 12 times 2 times 2, 1.33. About its end, 1/3 ml squared. So that'll be 4 times that, 5.33. Okay, so it's the same rod, but based on where the axis is, the inertia will change. All right. So now we have these 3 problems. Maybe take around, I don't know, 5 minutes on these. These are a bit tricky. All right. So I'm gonna go through these problems now. I know they're a little bit tricky. So the first one, moment of inertia about axis A, which is perpendicular to the square, is 6 kilograms times meter squared. What are the moments of inertia about axes B, C, D, and E? So for this problem, it seems like all B, C, D, and E, all of them, are parallel to the square, while A is the one that's perpendicular. So we refer to the formula where IZ equals IX plus IY. Okay? So now what do? Well, we know that A is the perpendicular axis, so it will be here. So I of A equals, well, what are our X and Y's? Well, the X-axis is perpendicular to the Y-axis, right? So if we choose any of these axes that are perpendicular to each other, then we can just plug these into the equation. Well, axes D and E are perpendicular to each other, so we can set those as the X and Y axes. So ID plus IE. Okay, so now we have this form. We have this equation here. Okay, so now what? Well, let's look at the diagram a little closer. So let me draw it like this. So axis E is here, axis D is here. So since it's a square, it's completely symmetrical on all sides. So it seems like by logic, the inertia about axis E is this exact same as the inertia about axis D, right? Because all the mass is distributed equally along both of them, because the square is symmetric. All right. So basically, since IE equals ID, IA equals 2 times ID. So ID and IE equal 3. Okay. So now we got those done. Now let's look at C and B. Well, C and B are also perpendicular to each other. So IA equals IC plus IB. And using the same logic, the inertia about C and B are the exact same as well. So both IC and IB are also 1/2 of IA. So all of these, every single one of these, has the inertia of 3 kilograms times meter squared. Okay? Now for the second one, what is the moment of inertia of a square with side length L and mass M? Well, what we can do is, well, we know that the moment of inertia around this axis, that's what we want to find, that equals this axis times 2. So if we find the inertia around this axis, then we'll know the inertia times 2 equals the inertia around axis A. Okay? So what is the inertia about this axis right here? Well, we can think of the square as a combination of many, many tiny rods, right? And based on what we know of inertia, if we just add all the inertias of these rods together, we'll get what we need. We'll get the inertia of the whole square, okay? So the inertia of each rod, let's say each rod is 1/n of the entire square's mass. Okay, so each rod has m/n. Okay, that's its mass. Okay, and then its inertia is therefore 1/12 m/n times L squared. Okay, that's the inertia of each rod. Okay, now we add all these inertias together. So we have n rods. So if we multiply this by n, we'll get the inertia of the entire square. The n's cancel, 1/12 ml squared. So that's the inertia around this axis here. If we multiply that by 2, we'll get the inertia along axis A. So 1/6 ml squared. Okay? So that was a bit tricky. Now for the last one, this is just a direct application of the formula I nu equals I0 plus md squared. All right, I0, let's set I0 as here. We know what that is. That's 1/2 mr squared. Md squared, well, the distance is here, and the distance is r, so it's just plus mr squared again. If you were to solve for this, you would get 54. All right, are there any questions about these? All right, so it seems like I do have more things to talk about, but since it's already 9 o'clock, we'll save those for next time. All right, so that will be the end of this class. If you guys enjoyed, I'll see you guys next time. Okay? So next time we're going to continue with our explorations with rotational motion. See ya.
Thank you. Bye.
Bye.
Bye.